An ice fishing sleeve is a cylindrical tube that extends from the floor of a permanent ice house to the top surface of the ice, preventing an ice hole from freezing over due to wind and snow. The objective of this project is to design an ice fishing sleeve to accomplish this purpose, along with the development of its manufacturing plant. The ice sleeve design has to meet 7 overall constraints, which include dimensionally adjustable, insulated, not impinging on current patents, environmentally friendly, durable, manufacturable, and marketable. In addition, a separate device objective was investigated to see the feasibility of an added device to prevent ice formation without added heat. 4 major device constraints were developed, which included non-invasive, low power consumption, reusable, and affordable. Catch Cover and Fish Hole Buddy are the 2 competitors on the market today. Their sleeves are very similar in design and feature a fixed height sleeve with thin walls.
With our project objective, we moved on to patent and market research to more clearly define our design constraints. To get a better understanding of the market we were going after, the team attended the Winter Sports Expo in St. Paul. With all of the information we obtained from research and attending the Ice Expo, we came up with 5 initial sleeve concept ideas, which we narrowed down to 2 final concepts. Both of these 3 designs include 3 sections that allow the sleeve to telescope down to the surface of the ice. The first of which includes 4 protrusions, or fingers, that stop the sleeves from falling out through the top. The second design accomplishes this through the use of a gasket that will be overmolded into the outside sleeve. Our lid design incorporated a fan that served as the device to stop ice formation without added heat. We were able to create full-size 3D printed prototypes of our sleeve designs through the use of the NDSU Mechanical Engineering Department facilities.
The first step in the experimental setup was to auger a hole into a tote that had been previously frozen with water. The hole was then filled with water to simulate an ice fishing hole. The tote was then placed on a pallet underneath a box. The box was insulated to act as a consistent control volume. The whole setup was then placed in a walk-in freezer, and a radiant heater, thermostat controller, and thermocouplers were used to control and monitor the temperature in the control volume. 2 main tests were conducted, a stagnant heat test at 60 degrees and a test at 50 degrees incorporating a fan in the lid. Both sleeves failed to prevent ice formation during the stagnant heat test at 60 degrees. 50-degree test with a fan, only the carb tank sleeve prevented the formation of ice in the ice hole, concluding that the designed carb tank sleeve outperformed the competitor sleeve.
The team was then tasked to develop the manufacturing plan to produce the sleeve. To do this, we investigated materials, manufacturing processes, and prices from multiple manufacturers. The 2 final processes determined to be used were structural foam and injection molded plastic, both of which use the same injection molding process that is capable of making all sleeve and lid designs. Additionally, the production of the lid fan assembly consisted of researching and quoting materials and assembly costs. All the quotations, bills of materials, and manufacturing costs were economically analyzed and presented to the sponsors to proceed with at their will. Prior to full production, additional testing will be required in a real environment. This will allow for any slight design modifications and business decisions to be made. We would like to thank Pat and Bob Staples for the opportunity to work with them in this project, as well as all others that assisted us throughout the year.